In today's class, we're going to be looking at one more example of a problem which can be solved using dynamic programming. It's called matrix chain multiplication. So before I explain what the problem is, I'm going to give you a fact now. Multiplying an m cross n and an n cross p matrix requires m into n into p multiplications. So I'm not going to give you a mathematical proof of this fact. It is simple. You can take matrices with small dimensions, say a 2 cross 3 and a 3 cross 1 matrix, and you compute the matrix product. You keep track of how many multiplication operations you performed. You will see that it is 2 into 3 into 1, which is 6 multiplications, and that can be generalized for any m, n and p. So multiplying an m cross n and an n cross p matrix requires m times n times p multiplications. So knowing this fact, it can be inferred that a series of matrices, when multiplied in different relative orders, can require different number of multiplication operations. So what does the statement mean? You have 4 matrices A, B, C and D. You want to compute the product A times B times C times D. Now when I say relative order, this overall sequence is going to remain the same. A, B, C, D is not going to change into A, D, C, B or something like that. It remains A, B, C, D, but within that, which 2 matrices do you multiply first and then which do you multiply to it, if you change that sequence. So for example, if you do A into BC into D, so you did BC first, then you did A times BC, then that whole product times D. Or if you did AB first separately, CD separately, and then you did an AB times CD. So within the sequence of matrices, if you relatively do some regrouping and compute the product, depending upon how you regroup, the number of multiplication operations required will be different. So if you are not convinced of this fact, there is an example coming up on the immediate next slide, so hold that thought for a while. Note that the number of multiplications depends only on the orders. It only depends on m, n and p, and not on what are the actual numbers present in the matrices. Now I'll give you first an example to justify this claim I have made, saying that if you regroup the terms, then the number of multiplications will be different, and then we'll come back and see what this problem is asking us to do. So you assume we have 3 matrices A, B and C. Their orders are 30 cross 40, 40 cross 50 and 50 cross 10 respectively, and the overall matrix product you are asked to compute is A times B times C, which, as you can see from the dimensions, is a compatible product. So now the first alternative is A times B times C. So you compute the AB product first and then you're going to multiply it by C. So now if I multiply in this order, I want to know how many multiplication operations I will need. So using this statement, this rule which I gave you, we first compute A cross B. A being 30 40, B being 40 50. So AB requires 30 into 40 into 50 multiplications. Now the matrix AB which you have is a 30 cross 50 matrix, to which you have to multiply C, which is a 50 cross 10 matrix. So that will require 30 times 50 times 10 multiplications. So if you want to compute A, B, C in this order, it will be 30 times 40 times 50 plus 30 times 50 times 10, which is 75,000 multiplications. On the other hand, if I wanted to compute the same product in this order, so I do BC first and then I do an A cross BC. Let's see, BC, B is 40 times 50, C is 50 cross 10. So BC will be 40 into 50 into 10, and your BC matrix is going to be 40 cross 10. Note that this is the number of multiplications required to form that matrix, and this is the dimension of that matrix. So now you have BC and then you do A times BC. So A is 30 cross 40, BC is 40 cross 10. So A times BC requires 30 into 40 into 10. So if you did ABC in this sequence, it would mean 40 times 50 times 10 plus 30 times 40 times 10, which is a 32,000 multiplications. So you can see that simply by identifying the correct order in which to multiply matrices, you are able to bring down the number of multiplications to almost half. So 32,000 can be thought of as almost 50% of, close enough to 50% of 75,000. And as you know, when you're working with data, it's highly likely that your data is going to be in the form of matrices. it is even likelier that those matrices are going to be large, huge. So it is important to identify the optimal sequence of multiplication, or where to put the parentheses so that the number of multiplications is minimum. That is exactly what the matrix chain multiplication problem asks us to do.